Hello and welcome to this video about Simpson's 3/8 rule. In this video we'll derive this numerical integration scheme using matrices. It tries to find a degree 3 polynomial to match 4 equidistant points placed on a curve whose exact function is unknown. It tends to be unstable and should only be used for gentle curves where there aren't any sharp bends, or for functions whose higher powers diminish, or it can be used when the interval width is small enough to get rid of sharp bends in the curve. It can be much more accurate than the trapezoidal or Simpson's rule when it is used correctly. On this graph you can see 4 points, and the area has to be calculated underneath it. We can interpolate these points to find the polynomial of degree 3, which passes through all 4 of these points, and then integrate this polynomial, thus finding its area. The polynomial is written on the left-hand side with coefficients of a0 to a3. We can substitute the values of these points into this polynomial to create 4 equations of y as a function of 0 to 3. Then we can pack these 4 functions up into this matrix equation. Evaluating all of the entries of this matrix gives us this equation. We can use matrix algebra to make the coefficients of the function into the subject of this equation. Then we can evaluate the inverse of this matrix, giving us this matrix equation. So now we have to find the area under the curve using this integral equation. Integrating this polynomial gives us this equation. And then we'll substitute these numbers in, which are the upper and lower bounds, 0 and 3. This is the area under the curve. Simplifying this expression gives us this. And this can be packed up into this matrix equation, which is also a vector equation. Now we have these 2 equations from which to derive Simpson's 3/8 rule. Substituting the first equation into the second gives us this equation. Multiplying this row vector by this matrix gives us this row vector, so we can get the area under the curve using only the heights of the function. The coefficients of this function a0 to a3 need never be known. We can multiply these 2 vectors together to give us this equation, which is Simpson's 3/8 rule for one segment. We can use it for multiple segments, but its ends will overlap, and the equation would need to be adjusted for this. So I'll just write the formula and graph out here at the top of the screen like this. We can see on this next graph that the shape of this curved segment, and therefore its area, will be invariant after translation. So this formula will work no matter where the points are located horizontally. And it will be preserved with rescaling. H will represent the interval width, and will be inserted into this formula to give this more proper formula for the curved segment. I know that this isn't a properly rigorous derivation because the points would have to be generalized to be x0, y0, x1, y1, and so on, but we could get away with this derivation because we knew that the answer would give the result that it did. Multiplying the 2 matrices together would cancel out all of the messy algebra to give a nice numerical row vector. You could easily write a computer program to derive this rule, and any rule that is higher than this. It should give good results for any theoretical gentle curve like the logarithm of x and 1 over x. So I hope that you have enjoyed this video. Please like and subscribe, and type your thoughts and ideas in the comments.